It is a pleasure to welcome you to the third edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The International Workshop on Unsaturated Soils was hosted in 2022 during the third edition of the AGERP lecture series. The following lecture on hydraulic characteristics of partly saturated clays was delivered by Professor T.V. Bharat at this workshop. Dr. T.V. Bharat is currently a professor of civil engineering at Indian Institute of Technology, Guwahati. He has received both his MSc and PhD from the Indian Institute of Science, Bangalore, in 2004 and 2009, respectively. He worked as a visiting fellow and postdoctoral fellow during 2009 and 2012 at the University of Saskatchewan, Canada. He started his teaching career as assistant professor and, subsequently as, associate professor at IIT Guwahati from 2012 and 2021. Dr. Bharat has nearly 20 years of research experience and 12 years of teaching experience in India and Canada. Dr. Bharat has published over 60 peer-reviewed journals, book chapters, and conference papers. He has received numerous awards in India and abroad for his contribution to computational geomechanics and geoenvironmental research. Dr. Bharat is the editorial board member of the Indian Geotechnical Journal and is an active reviewer of over 25 peer-reviewed journals. Dr. Bharat's research interests are waste management, mitigation of rainfall-induced landslides, and geotechnical and architectural aspects of heritage structures.
Good morning, good afternoon, good evening, all the participants across the globe. And first of all, I'm delighted and honored to be invited to this series of workshop series on unsaturated soils under the aegis of third AGERP 2022. And today I'm going to speak on hydraulic characteristics of partly saturated clays. So when we introduce the unsaturated soils, first we need to discuss about the hydrological cycle, because we live here in the hydrological cycle in this particular nature, where this evaporation that takes place from the land and transpiration, and also the precipitation that takes place and the groundwater flow takes place. And when all these things are taking place around you, there's a active zone where some part of the land which is partly saturated condition. So when we are living on this partly saturated condition, partly saturated soils, and the changes that occur to the soils due to the climatic changes are changes that happen in the nature, they have to be taken care. We have to take care of these things in the engineering design and analysis, definitely. And when we talk about the applications, because this is a major debate that happens every time when we talk about the unsaturated soils, that is there any application of unsaturated soil mechanics? But when we talk about the applications, the physics of unsaturated soil behavior has evolved way long back, before the beginning of soil mechanics formally introduced to us, our engineers. So in the soil science, the permanent wilting point is a point which is important for understanding the wilting of the crops. This is related to the suction of the soil. And the suction of the soil, which is close to the residual suction corresponding to residual water content on the soil water characteristic curve, and wilting starts taking place. So this is something to do with soil moisture or suction. So a lot of research has been done in this direction to understand, measure in the field what is a soil suction. So most of the techniques currently we use in our engineering are derived from there. So similarly, the plant stress is related to the abiotic stress factors, and which is related to, again, lower high temperature. So thermal related issues, thermal related aspects in soils, and deficient or excessive water. So that is related to, again, hydraulic mechanism in soils. And similarly, high salinity are heavy metal things. So these are related to osmotic effects in soils. All these are studied way back. And so they have been well understood. And a lot of research has been done in these directions in other disciplines, such as soil science, way before, earlys of 1900s are little even before. Similarly, in the other disciplines like hydrology or water resource engineering, the prediction of flood occurrence is related to the soil moisture. If you see, when there is a flash floods taking place in some parts of India and other places in Asia during November and December, so this is immediately after the monsoon or rainfall, heavy rainfall. Once the rainfalls have subsided, and when the again rainfall starts in the month of November, December, which is temperatures are also low, and evaporations are less, and a lot of moisture in the soil. And during that time, you will generally see that the flooding takes place. So most of the casualties due to the heavy rainfall events are, when they occur in the November and December, they are very heavy. So this is because of the soil moisture. So the soil moisture is a very important factor for them. And in fact, how to evaluate the soil moisture, and are from the satellites or something recently, or from the field data directly. So this has been already widely understood. Similarly, the evaporation potential for the groundwater availability, all these aspects have been studied very well, and it requires unsaturated soil principles. So the same concepts have been taken into engineering to understand one important aspect is landslide events. So if you see, this is a natural slope that exists in one part where you have a certain Vado zone, a partly saturated zone that exists here. And if rainfall takes place, so there's a runoff that takes place, and also some surface water, which also gets in slightly, there's an infiltration that takes place, and then this water actually gets into the surface water. So, but then due to the development of infrastructure, we often construct certain roads or something, and then where we make infrastructure developments as roadways or railways. So to make that, we cut the slopes, and on the upstream side, we try to protect the slope, and on the valley side, generally this is left without any measures, or sometimes this is also protected using breast walls or something. So in the basic geoengineering aspects, when we see, so here, if the weep holes are generally choked, if proper filter material is not used, or some other reasons such as maybe development of vegetation, etc., through the weep holes. Generally, if these particular pore pressures, high pore pressures are developed on the upstream side, then you see that the failure takes place on this upstream side. And this is one of the examples where similar slope is shown. This is in Assam, where currently I reside, near the Shillong bypass. And you see that this is entirely one hill slope, but a roadway is made. And you see that here a huge failure has taken place on the valley side, because although there is a drain that exists, surface drain that exists to channelize the surface water towards other side, but the water which percolates into the ground through the subsurface and which comes out, and you can see the daylighting of water in certain time zones. For example, during the rainfall events, you see that there are daylighting of water in these particular locations. So we are actually creating, if we are not very well aware of the consequences that happen by obstruction of the flow of water, and the two partly saturated water, I mean the unsaturated principles are not met, and you see that a lot of destruction that takes place, not just on the valley side or on the upstream side, but also you see that underneath the road, for the first time, the soil underneath this particular road, this subgrade, experiences wetting under the stress conditions. So you will see a destruction sometimes as well. So this is another valley side failure in a nearby state called Meghalaya. So these are some of the problems that I was just mentioning underneath the pavements, because the water which would ingress into the slopes and would actually detour under the existing natural pavements, and then when the wetting takes place, either subsidence takes place or heaving takes place. So depending on the type of soil that exists. Oliver would have mentioned the collapse behavior, etc. And then these places, you see that excessive amount of kaolin present to a deeper depths. And kaolin, when it is in the dry state, it can take a lot of mechanical stress. But when during wetting, it immediately collapses, immediate collapse, in fact. So this is the destruction of the infrastructure that has taken place due to that reason. And similarly, when you see a lot of valleys and which is actually surrounded by a lot of hills all around, there's a beautiful place in Assam where we reside, and maybe just 7 hours drive from here. And the current situation, just a week ago, this is the situation, the debris flow takes place. A lot of rains have been happening since February, March, but however, the rainfalls that occurred during the month of May have destructed the whole thing. And in fact, the entire debris has flowed down the hills, and in fact, they've submerged all the trains and a lot of passengers and other things. So this destruction is eventually the soil moisture levels related to the soil moisture levels in the slopes. Definitely, this is not something to do with unsaturated soil principles. Similarly, the bank failures, often people study, and in the landfills, the cover system, which is made up of bentonite plus sand, if proper design is not made, the infiltration characteristics are not properly met, and the capillary barriers, because of the capillary barrier system, and the excessive water pressure will be generated within the top layer, and it can actually slide down and it can cause a disaster. So again, the unsaturated soil principles are required in this aspect. And this is one of the important area where a lot of people study how to the repositories, the design of nuclear waste repositories for safely disposing of the radioactive elements or nuclear waste, high-level nuclear waste. So this is generally done at very deeper locations, maybe at more than a kilometer or so, and then they actually make access tunnels and then reach to the particular location and keep the radioactive elements. They place it in the canisters, and then they compact it with the bentonite layers or the backfill with bentonite blocks all around. So here, the flow behavior through the bentonites and also the swelling pressure that generates due to the wetting, these are very important. And in case if there's a breakdown of the canister and the high level radioactive elements that actually diffuse through the soils is also a very important aspect that has to be considered in the design of safe disposal of the radioactive waste elements. So in this, the understanding of the flow behavior through the compacted bentonites is vital, and that too in our constrained environments and also partly constrained environments. Similarly, this is an important application where in the drought hit regions, to retain the water in ponds, so you can have a bentonite plus sand layer, and this would retain the entire water, and because otherwise the water would have percolated into the deeper layers, and this is not reachable to, or this cannot be extracted from the ground. So this can be retained using the simple mechanism of the capillary barrier. So even after the breakthrough, because sand is dry in the beginning, so water simply tips down, and again sand is in dry condition. So only small water, because we know the saturated hydraulic conductor, the bentonite, and because of the which is less than 10⁻⁹ meter per second. So very small amount of water percolates through the sand layer, and then because of the capillary barrier, it actually suspends, water gets suspended at the interface. This is the project I handled 10 years ago. And similarly, capillary barriers, which is it's catching up currently, and then which is popularly used in Singapore. And we had a lecture by Professor Rojas yesterday, and then I'm not discussing about this. But you have plenty of applications, but the basis for this flow behavior is again from soil science. This is not very new, though what we have understood after the developments that have taken place in other disciplines. So the major contribution, if I feel I can actually note down, is the development of effective stress principle by Bishop, because of the Bishop's effective stress principle, which can be used to understand the shear strength behavior of partly saturated soils, and later on whatever the developments have taken, that can be summarized into the same effective stress principle that was given by Bishop. So this could be the only, maybe the best contribution, independent contribution that was made in geotechnical engineering, I feel. So coming to the flow, I'm interested in discussing about the flow behavior in clay soils, because the flow behavior, a lot of misconceptions are there in understanding the flow behavior in soils in geotechnical engineering. I'll try to address those issues today. So when we discuss about flow behavior or any other behavior or any observation that we make to develop a mathematical model to understand the behavior, first thing we need to understand these fundamental principles. So we have certain governing equations such as mass conservation, linear moment conservation, angular momentum conservation, etc. So these are the fundamental equations that have to be satisfied in any formulation of mathematical problem. So first we have a physical observation, then you talk about a governing equation which is responsible for the physical observation. So you pick, for example, if there's a flow that is taking place through a mass of soil, then you have to pick the conservation of mass. And if there is a swelling also taking place at the same time, then you also pick the conservation of linear momentum. So that is a force equilibrium also has to be considered. And then you formulate the governing equations. And these governing equations are not sufficient to solve your problem, because there are material related uncertainties that come in. So you require additional equations. For that, you identify the state variables. For example, when you talk about the flow through the unsaturated soils, we consider the conservation of mass. If the flow takes place through a soil mass where there is no volume change that takes place, our force equilibrium is satisfied, then we consider the conservation of mass. And if you combine with the Darcy's law, what you get is a Richards expression, which is given in 1911. Then when the soil mechanics is not formalized as a separate subject. So here the dependent variables are the state variables are the matrix suction head and volumetric water content. So we need to have relations between these state variables for deriving constitutive relationships. So because constitutive models are required to understand or to bring additional equations to solve these equations. So what we bring is the relationship between HM, matrix suction head, and volumetric water content, and hydraulic conductivity versus water content. So these are the constitutive models, soil water characteristic and HCF. So after knowing the constitutive models and identifying the middle constants, which are the equation constants in your constitutive relationships, you try to predict the behavior. So if prediction is not accurate, you go back and then understand what additional equations are required for your model. So this exercise is very, very important, and this will be utilized in this particular presentation to understand some of the loopholes currently we are having in understanding the flow behavior through soils. So if I go back to the Richards expression, so this is a partial differential equation, and there are two constitutive models here. One is hydraulic conductivity function, another one is soil water characteristic curve. So soil water characteristic curve is a relationship between matrix suction or matrix suction head on x-axis and volumetric water content on another axis. So this equation is in fact similar to your effective stress versus void ratio, because similar equation, as effective stress increases, the void ratio decreases. So similarly here, as a matrix suction increases, the volumetric water content decreases. But however, there's a hysteresis, and the drying wetting behaviors are different. So this is similarly, you have a hydraulic conductivity, which is related to the matrix suction. And so this behavior is also similar. And often we have statistical models or pedo transfer functions to derive hydraulic conductivity functions from the soil water characteristic of itself, knowing the pore size distribution models. Generally, these are pore size distribution models, right? So just before going into those discussions of soil water characteristic curve and other things, let me first briefly explain what is soil water potential or suction. So suction or soil water potential is for partly saturated soils is a negative value. The soil water potential is a negative value because the potential for, because of the capillary forces or capillary potential, because when you have a capillary which is existing, then it sucks the water because of the surface tension forces, or we can call adhesion forces that also predominate. Similarly, when you have a clay system, when you have diffuse layer system, and initially when you have exchangeable cations on the surface, and when you bring water or bring the particles into the water, the ions can diffuse away because the concentration of the ions near the particles are high compared to the bulk solution. So the ions should move away from the particles, but because of the electrostatic attraction and the affinity towards the ions cannot move away. So then water has to come in. So water is sucked. So suction, water is sucked into the close to the particles, and so in fact, because of the development of the osmotic potential, in fact, they can swell also. The swelling mechanism in clays is because of this reason, because there's an osmotic potential that is available. So there is a capillary potential, osmotic potential, similarly hydration potential. So the particles get hydrated when water is available, and similarly when from the rest state also, from the atmosphere, water can be absorbed and then it can be retained on the surface. Similarly, the ions also can get hydrated. Majorly, the soil water potential or matrix suction, which is positive quantity, consists of these three mechanisms: capillary potential, osmotic potential, and hydration potential. Often we only consider the capillary potential, and recently there is a lot of interest in understanding the osmotic and hydration potential of clays. So certainly there is a difference when you consider sands or any other silts and sands, coarse grained soils, or even fine grained soils which are not active clays. Then capillary potential is the major dominant phenomenon that controls suction in the soils. But when you have active clays, the osmotic potential and the hydration potential also significantly contribute to your suction. Now, we often, to establish the SWCC for the flow behavior, we have several equipments or instruments, and starting from tensiometer, axis translation, osmotic, etc. So many things are there. Most of the techniques have been developed in soil science, and then we have simply taken and we've been using it. So they have some practical limitations in using them, and often you see that the tensiometers are very handy. You use it in landslide monitoring systems where you just simply push into the ground and then keep monitoring the suction values. So similarly, of course, you also measure the volumetric water content or moisture contents. So often recently, but because the tensiometer has a limitation, that maximum value, it is theoretically 100 kilopascal, but it could be less than that depending on the atmospheric conditions, RH, etc. So because the cavitation pressure controls the maximum range of tensiometer application. Similarly, the fixed metric porous ceramic disc, which is understood to be, which is claimed to be measuring the suctions in the whole range, these two are widely used currently in the field because others cannot be used in the field. They're all laboratory techniques. So to measure the matrix suction, but is it really so? if I take a tensiometer and the porous disc, higher entry porous disc, and if I place these two things in the soil, embed in the soil along with the soil moisture sensors, often a lot of researchers have in fact estimated the soil water characteristic curve by under the submerging conditions, and then simply measuring the suction values instantaneously, they have established soil water characteristic curve. If we do that, what happens? Let us see. First of all, the measured suction values are the rate at which the suction changes, because these are all instantaneous values. The equilibrium value is what you require. They keep changing depending on the initial moisture content within the soil and also the initial condition of the sensor, whether sensor is wet or dry and soil is wet or dry. If it is wet, what is the percentage of wetness or moisture content that is available? Based on that, in fact, the tensiometer itself, which requires a huge equilibration time, and in fact, in some cases, it can be even 10 days for compacted clay soils. Compacted clay means this is a lateritic soil. From one of the hilly areas, we have extracted the soil, taken the soil and then compacted it in the laboratory and then measure the moisture contents as well as the suction values. But here only the suction values are shown because moisture contents are very good. Moisture sensors are very good to instantaneously measure the moisture content. There is not a big problem with the moisture measurement, but suction measurement is a huge issue. If I try to establish the volumetric water content versus suction in this manner, because it's a very fast process, in an instantaneous process, within 30 minutes, I can obtain the entire suction profile and water content profile. So then immediately I can draw the suction values corresponding to given water content, and then I can establish the soil water characteristic. And this is an equilibrium approach which takes around 60 days for one particular soil to establish the soil water characteristic curve, because you see that it has reached equilibrium. After that, again, you've change the water content of the soil. Again, you change the water content of the soil. So it takes time in each step. So in this way, it takes an enormous time. What you see is when you predict the landslide or the factor of safeties, and you see that even the instantaneous approach, which is highly conservative, which doesn't even predict the landslide until the 220th day or so. But the equilibrium approach, which predicts within the 27th day or so, and this is exactly matches with a field observation. There is a failure that has occurred in Meghalaya. So it seems that even these approaches are similar for the porous fixed matrix porous ceramic disc. In fact, this takes enormous more time, especially in case of active clays. So with this observation, let us move on. In case of clays, when you have, so you have certain active clays. So these are all Indian bentonites, and you have granulated bentonite, which is taken from GCL, because GCL is also have wonderful applications in landfills and other containment applications. And this is a natural clay, active clay from one of the regions in South India, Kuttanadu clay it's called. And this is from Jabalpur, which is a black cotton soil. And if you see the liquid limits, they are quite high, because obviously this is a bentonite, a high quality bentonite, which has a liquid limit of 597. The specific surface area and cation exchange capacity, and then the type of exchangeable cation that is present, in fact, influence the consistency limits of the soils. And now the question arises, if the estimation of SWs is so complicated in case of silts or low plastic clays, then what happens in case of high plastic clays? Because these two constitutive relationships are important for estimating the flow behavior through the soils. There's one particular technique called osmotic technique, which is also available in the literature, and which is quite handy in those cases, because plastic layers can be just simply put it in semi-permeable membrane and then tie it and then place it in the polyethylene glycol solution, PEG solution. So PEG solution has certain concentration, and the initial state of the soil could be anything. For example, here the bentonite, Indian bentonite is placed here at water content 1.5 times the liquid limit water content consistency. So this is a fully saturated soil. When it is kept in the PEG solution, the PEG solution has certain concentration, so that it has certain potential, and potential here is 0. Negative potential is not there. There is a 0 potential. So here potential is lower because higher concentration of PEG solution. So because of potential drop or potential difference, water is drawn from the soil, and then water comes out and PEG solution concentration changes until there is an equilibrium between the potential in the soil and potential in the PEG solution. So if you can measure the potential or suction value or the concentration of the PEG solution, we can understand what is the suction in the soil at equilibrium. So there is a important correlation that has been given by Delige et al. And there's a concentration of PEG solution and then the square root of suction. So this relationship could be used to understand what is the suction level in the soil by understanding the concentration of the PEG solution. We can get the concentration of the PEG solution using refractometer. So you can measure the Brix index, which is in fact used in alcohol quality, and same thing could be used here to measure the concentration. From the concentration you can estimate the suction values. So similarly, here one thing is that there is a limitation again. So you have a maximum concentration that you can go for, and also the pore size cutoff value of the membrane. And here hardly you can go for about 2000 kilopascal, but if you go for 6000 cutoff value of the membrane, and then larger than that, you should have the PEG molecule size, then you can even go for 4000 kilopascal suction range. So beyond that, if you want to go, you require a vapor equilibrium technique. So where the vapors of these salts can exhibit a huge very low RH. So as low as 11.3 RH, and corresponding temperature could be 25 or anything that could be maintained. And from the Kelvin's equation, you can estimate what is the suction that is imparted on the soil. So you will have a saturated salt solutions underneath, and you create a RH environment, just like in air-conditioned room. When you are sitting, you feel thirsty because RH is low, around 70 or so. So that much suction is exerted on you on your skin pores. Similarly, the soil is experiencing certain RH, so water has to be left because it has to come to equilibrium with the atmosphere. So similarly, you can estimate the suction values. But in case of these active clays, you also require the volume changes that happen, and which can be estimated independently using Claude method or something, where you can coat the even Fevicol or any other glue, polyvinyl acetate glue, PVA glue, you can coat, and then you can directly dip it in water or kerosene, and then you can measure the volume, displaced volume. From that, you can estimate how the volume is changing in the soil sample. So this way, it is possible to estimate the gravimetric water content, because that is what we are actually estimating by weight, and controlling the suction values. So this particular data are from osmotic technique, and this is from vapor equilibrium technique. So when you combine with the volumetric shrink S-curve data, you can obtain the degree of saturation versus matrix suction. This is a plot which is required. But here, one thing what we have done is here, the volume is not constrained. Volume is simply allowed to change. So this way, in fact, you can get a number of cycles. There's a initial drying, and then you can get a primary wetting, and primary drying, secondary wetting, all those cycles, in fact, you can get. But there is a catch. I will soon explain. So what happened in compact conditions? In compact conditions, similar experiments can be conducted with PEG solution and vapor equilibrium techniques, where salt vapors are circulated around the clay sample so that it comes in equilibrium, and then it achieves certain suction value or water content. So we can, by weight, we can measure the water content, and the salt solution RH, we can, in fact, the salt solution directly can be taken and then kept under the WP4 or dew point potentiometer, and you can measure the RH values directly, and you can estimate what is the suction that has been imparted on this clay sample, and you can establish the soil water characteristic curve. So, but then one issue with the PEG solution osmotic technique is that longer exposure of PEG solution with the membrane can cause damage to your membrane, and PEG can enter directly into the soil. So especially after 10 to 12 days, the PEG solution can directly enter because of the attacks on the microbes. Again, there's a lot of research that is going on currently, but in the 70s itself, there is a solution for that. You can use penicillin along with the PEG solution so that it can actually prevent the microbe attack. And then it can be used even for 30 days or so, because coming to the equilibrium, it takes longer time in a compacted bentonite system. So here for the compacted bentonites at different densities, I'm showing you the relation between grammage content and suction values. And these are from osmotic technique, these are from Weber equilibrium technique for different densities. And when you directly convert into degree of saturation versus suction, because it is easy, because volume is constrained, volume is constant in your case. So I don't need to estimate how the volume is changing using any other technique. So volume is constant, so I know what is a wide ratio, and I know what is the water content, and rho s anyways, I know the specific gravity or density of solids. And if I estimate, interestingly what you see is that the degree of saturation goes beyond the 100%. So this is not an isolated observation from our group, but some researchers have also observed, like Villar and other people have observed, other researchers have observed the degree of saturation goes beyond 100% in bentonites, compacted bentonites. So what could be the reason? So this has been again of great debate or great interest in the soil science. So this is mainly attributed to changes in the density of water. So the density of water which is considered here is 1 megagram per meter cube. And when you consider that, the degree of saturation estimated close to the saturated state is around 130%. This is higher density, this is lower density. And it meets the 100% saturation line nearly at 10 MPa or so, between 5 MPa and 10 MPa, right? So this observation is very interesting and is attributed to the changes in the water density. In the literature, if you see, since 1960s in the soil science, they have observed that water densities can even increase beyond 1, and they even go to 1.4 megagram per meter cube, where water content is less than 10% in bentonites or montmorillite clays, and also in kaolinites. And the approach 1 megagram per meter cube or less than 1 megagram per meter cube with increase in water content, as observed by Richards and Bauza, and using several experimental observations. These are experimental observations using helium gas displacement spectrometry and buoyant force measurements that have been done, and they have measured how the density of water is changing with change in the water content of soil. So, but then all these, most of the observations that are available are simply you take few particles and then try to measure how the changes in the density are happening, not the compacted system or when you have a small spore and micropore and macropore system, right? So these are some of the observations on bentonites and MX80 bentonites, how the density of water changes. So with increase in the water content, they come close to 1, right? And so this is an observation that was made by Lauret for FEBEX. This is going beyond 1. So there were some attempts how to correct the degree of saturation for clays. So that was proposed by Willard in 2005, and the correction is essentially based on the concept of liquid multilayer structuring. If you have a clay particle, close to the clay particle, maybe the first layer of water, which is strongly adhered to the clay particle, will have a density close to 1.8 megagram per meter cube. And if you are going away from the particle, the water content, the water density decreases and achieves 1 at bulk solution. So you take mean values because number of layers of water molecules that exist around the particle, and first layer, then it is 1.8, and few more layers, then average of 1.8 and 1.5, like that. You can take mean values and then you can correct it. That's how the corrections have been made. But if you see such corrections, the important observation what you get is the water entry point, which is similar to the air entry suction. The water entry suction is nearly negligible. There is no water entry for compacted bentonates, right? Is it something strange? Water entry should be very high. It should be around 10 MPa or 5 MPa for bentonates. But here, this is negligible amount. This is even a few kilopascals maybe, right? So from our measured Indian bentonates data, if you see, if I bring this, especially the degree of saturation should be 100% at any given point. So if you adjust these points to 100%, then you can estimate what is the density of water. If you back estimate the density of water, what you observe interestingly is that close to the saturation, the density is very high, around 1.3. Here it's 1.3, here it's 1.2, here it's 1.1, here it's 1. But this should be opposite, because higher water density should be there at higher suction or low water content, and lower water density or close to 1 should be there near the saturation. But this is an opposite behavior. So there is a huge debate that is taking place, how to adjust or how to understand these behaviors. And currently this is inconclusive. And with this inconclusive statement on SWCC of compacted bentonates, I move ahead and explaining about the hydraulic conductivity function, because these two constitutive relationships are required for the flow behavior. Just reminding you why this is required. So for coming to hydraulic conductivity function, it is a relationship between hydraulic conductivity with suction. Only method that is employed in the laboratory, popular method, is multi-step method, but this is not for clays. This is best suitable for sands or any other soils, because the volume of water that comes out due to the application of the suction is very, very small, which cannot be measured, and also takes enormous time in case of silts, and then you can forget about it. Good luck if you want to measure it for active clays. It's not possible, right? So this expression is actually an analytical solution of Richard's expression by considering D is constant with Z. So this is given by Gardner, and this expression is often used in multi-step outflow technique for estimation of conductivity. So another one method which is often receiving a lot of traction in geotechnical engineering or geoenvironmental engineering for compacted bentonates is the instantaneous method. Since 2009 or 2008, a lot of traction it has received. But if you trace back the origin, this is from Daniel, 1982, 1983. Further, if you trace back, it will go to 50s or 60s. The method involves very simple steps. So if this is a compacted bentonite column or sample, you cannot have a big column because flow behavior is very, very slow. Flux is very, very slow. So you cannot have a effort to have a very long column. So this is a small column, and psychrometers are placed at different locations on different sites on the perimeter of the column, and water source is allowed to go in, and then there's a vent. Instantaneously, you measure the relative humidity at any given spatial location within the soil sample when the water flow is taking place. So instantaneously you can draw how the water suction value is changing with time. Once that is known, you can establish the gradient by understanding how the suction is changing with X spatial location. Then the flow rate, average flow rate can be obtained by integrating how much amount of water that has gone beyond a particular location, that is say Xi, to L. L is this one. Beyond this location, what is the amount of water that got accumulated over given time. Based on that, you can get average flow rate, and by using Darcy's law, you will get the hydraulic conductivity. So this method is was used in for sandy loam, silt, tough plus bentonite, and other soils in 80s. This got a lot of traction for estimating the hydraulic conductivity of bentonites. So if you see the hydraulic conductivity or relative hydraulic conductivity with respect to suction, so the changes are as expected, because several orders of magnitude of hydraulic conductivity changes with increase in the suction, right? So increase in the suction to 10 MPa. So several orders of magnitude of hydraulic conductivity has changed. So this is an expected trend because this is a typical curve of hydraulic conductive function. But when it is applied for bentonites, this is Chinese bentonite, GMZ bentonite, Gomin's bentonite, and hydraulic conductivity versus suction, when it is obtained by this method, you will get a lot of discrete points, because this is estimation. Individual point you will estimate from the hydraulic conductivity K expression that was shown earlier. So two striking things here. One is the hydraulic conductivity change due to change in the suction of nearly 80 or 70 megapascals is only one order of magnitude for bentonites. Compacted bentonites from the saturated state, that is believed to be 10 power minus 13, which is not reported, I guess, and from there to 70 or 80 MPa, the change in the hydraulic conductivity is only one order of magnitude small or reduced. Second striking point, the hydraulic conductivity beyond 50 or 60 megapascals, it started increasing. The hydraulic conductivity is increasing with increase in the suction. So if you think this is an experimental error, but this is claimed to be a important breakthrough in the science. A lot of works, following works, in fact, also reported and supported this statement that hydraulic conductivity will increase with increase in the suction, that too at what suction? At around 70, 80 megapascal suction. That is when the water is existing as a thin layer, or only one layer of water molecules exists around the particle, and the density of water is around 1.8 megagram per meter cube. There it is found to be increasing. So this is claimed to be due to exfoliation of particles at that particular suctions. But exfoliation is like peeling off particle surface. But here, the hydration forces are too high at this particular suction, or the water molecules are strongly adhered, because of which only the density is 1.8 megagram per meter cube. The question is whether the exfoliation takes place. Some experiments using MIP, Oliver has given a excellent description of how the MIP should be used. And here, in fact, we have used freeze drying technique to remove all the water in the soils at different stages, and we have taken mercury nitrogen porosity values for establishing the pore distributions. So this is one profile where the volumetric water content is changing with the distance, and this is close to the source water reservoir. Sorry. Okay, if a soil sample is connected to a water reservoir, and this is close to the surface, close to the source, and this is away from the source, and this is at infinite distance. So at infinite distance, this is the initial moisture content only, and this is close to the source. So we have taken few samples from very distantly different from source. This is at A and B, C, D. When we measure pore size characteristics using MIP, what you notice is that they did not significantly change. The pore size are not significantly altered until when it got nearly saturated, where you get a unique peak and almost like it's flat. This could be possibly because the orientation of the particles into parallel plate manner. Because when initially compacted the bentonite particles, they arrange themselves into a flocculated manner, because there only you will have intraparticle and interparticle pores as seen as micropore and macropores. So once completely saturation takes place, the repulsive pressures will dominate. As I showed earlier, that the osmotic pressures will come in kickstarts, and because of the presence of the electrostatic forces, and the particles will turn parallel to each other, and they come parallel to each other. So almost you will see that a unique pore will exist, because this is representative of distance between individual particles. So that is what is seen at this particular point. But other than that, you will not see any distinct behavior of pore size changes at this particular 70 MPa, 70 MPa or something, where exfoliation takes place. How to resolve this issue? So one particular technique, which is age-old technique again, which is developed in soil science, which is called imbibition method, where you take a soil sample, soil column, and which is connected to a reservoir, and the water gets in, and you will have a wetting front somewhere here, and behind that there is a huge changes in the water content. Close to the water source, you will see that this is a fully saturated system, and away from this is a completely air dried, and in between you will have in between water contents. So using Boltzmann transformation, you can inverse the Richards expression. You will get the expression for d theta. D is the diffusivity, which is the diffusivity is nothing but the hydraulic conductivity times the slope of the SWCC line, pH by d theta. That is diffusivity, which is similar to your coefficient of consolidation in consolidation behavior, CV, which has units of meter square per second. Here also it has units of meter square per second. So you can establish or estimate the diffusivity with water content by using this particular technique. So here the lambda is the Boltzmann variable, which is x by square root of time. This x is spatial location and time is at any given time. At any given time, you have the volumetric water content versus x. Then this is constant. So this is simply a x of theta. The variation of theta with respect to x, that function if you integrate over dry state to saturated state, and then multiplied by again slope of this d theta by dx, 1 over d theta by dx, you will get the diffusivity at any given water content. This is also used in the literature for understanding the diffusivity of hydraulic diffusivity of several soils. So here, when we have utilized hydraulic diffusivity and when we use the soil water characteristic curve, and what you get is the hydraulic conductivity. And the hydraulic conductivity here, if you see, for many literature soils and our Indian bentonites, this follows a typical trend for any hydraulic conductivity function it shows. It doesn't increase with increase in the suction. So the increase in the suction, what you see is an observational error. As I mentioned earlier, the suction measuring techniques takes enormous time to establish the equilibrium between the soil, pore water, and the sensors. So when you are using instantaneous methods such as these, sorry to go back, when you are using these instantaneous methods to measure the suction, that too not even directly measuring the suction or dielectric constant or any other thing, but it is directly measuring the RH, relative humidity. So if you have any experience in measuring the relative humidity or suction values in a dew point potentiometer, will understand how much time it takes for equilibrium. But here you are measuring instantaneously the RH values, that too in bentonites. So which generally takes several days to come to equilibrium with your instrument, but you're completing an entire test within few minutes or to few hours. And that is the error that is actually propagated, and then you started observing that the suction values, with increase in the suction, hydraulic conductivity is increasing. In fact, interesting part is that there are several researchers, without understanding, maybe by falling prey to this particular observation, they developed models for hydraulic conductivity changes for decrease and increase with suction values. This is published in Geotechnical and other reputed journals. These are available. These things are available. So that is, I believe that this is purely a problem with the measurement of the suction instantaneously. And if you adopt this particular technique, you see that the suction values are, with increase in the suction, the hydraulic conductivity is changing in the manner you expect. A standard trend is followed. But the question comes now, how sure you are about this d theta by dhr, dh by d theta? Because diffusivity is fine. We have just simply measured, estimated from the water content observations. But hydraulic conductivity can only be established using the slope of the SWCC. But the slope of the SWCC for compacted bentonates is inaccurate because the water density is not corrected. How sure you are about it? But whatever the kind of slope you consider, the trend will be similar. Although it may be decreasing faster or decreasing slower, but the trend is similar. It cannot increase with increase in the suction. So still, I consider that this hydraulic conductivity is not accurate enough because the slopes may not be accurate without considering the density of water effect. So what I propose to use is, why to go back to hydraulic conductivity? Why don't we use the diffusivities itself? The diffusivity, when you consider with volumetric water content, they're consistently constant for any given bentonite quality. So the bentonite, the diffusivity is constant with change in the water content. So you will have a unique diffusivity. But if you see another fine sand or other soils, the diffusivity changes several orders of magnitude with change in the water content. But that is not the case with bentonates. So that means to say that your Richard's expression turns to your fixed diffusion equation. Your hydraulic diffusivity turns to self-diffusion of water in bentonite. So now this is much easier. So because we have dealt the contaminant transport problems where the diffusivity or diffusion coefficient of several species have been estimated. Here the same way the diffusion coefficient of water species can be established through bentonites, because the pore structure or this adhesion forces will predominate or dictate what should be the diffusion coefficient. And when it is constant, you can use similar methods what we use in the contaminant transport equations and to establish the d value, and now you can do the transport problems solve and without going for SWCC. Here you can overcome the estimation of SWCC, and there is no requirement of understanding what is hydraulic conductivity. You can estimate the d values and you can predict the flow behavior or theta variations and theta variations across the soil sample. So how fast this is moving, that can be established or understood, right? Similarly, this can be linked with the swelling pressure behavior, and you will have a generalized framework. And if it is a unconstrained state, you need to combine with conservation of linear momentum or force equilibrium. Therefore, you can establish how the d value is changing, at the same time how the swelling pressures are changing, or the swell volume is changing, right? So a lot of research is required in this direction, and then we have done some experiments, and then we got independently, we estimated the d values which are incoherent with the estimated diffusivities from the imbibition techniques. So which is not published yet. Soon it will come in limelight. So with this, I conclude that the instantaneous estimation of suction values by sensors is erroneous. We should be very cautious in doing that, because most of the applications, in most of the field applications like capillary barriers, when you are establishing capillary barriers for slope protection or any other applications in the cover systems of landfills, essentially you embed the suction sensor and then establish the continuous measurement of the suction you take, and based on that you measure the stability is met or not. But instead of that, if you can measure the water contents, because the water content sensors can quickly measure the water contents, the response time is very less. So based on the water content are established to the SWCC, you can get the suction values for establishing factor of safeties. Coming to the compact bentonates, the SWCC poses a big challenge because of the water density uncertainties, because water density values are not known how they change with amount of water content, especially when you have pore structure is evolving with change in the water contents. It is very, very difficult to understand, very complex to understand how the water densities are changing, because the forces that come in are van der Waals forces, Coulombic attraction, Coulombic repulsion, depending on the particle charges. And also you have electrostatic attraction, electrostatic repulsion, and all those forces combining govern the behavior of flow through the soils. So the best way for compacted bentonates is that, as of now, you can avoid completely establishing SWCC by directly establishing independent diffusivities. Just like you take a small soil sample, bring it to the laboratory, and you conduct a consolidation test. You establish CV, coefficient of consolidation. Now you estimate what is the rate of flows in soils, right? So because you got a material constant, based on it, you can understand how flow takes place. Similarly, a small bentonite sample can be taken, compacted, you can measure the diffusivity, you estimate the diffusivity. Using this, you can understand how the flow rates take place in bentonites. So essentially, it has to be combined for unrestrained case as well, and a lot of work is required in this direction. With this, I conclude, and I hope the presentation is useful. Those who are working in unsaturated soil flow behavior, and this is my, I should say, backbone for my research. These are my research students. I thank my students and the funding agencies. In this case, I said instead of correcting the water density for compacted bentonites, because that is very difficult at present. This is not completely understood. And there are certain procedures laid down, but I felt they're incorrect, or at least I don't agree with, as I mentioned, because the water entry pressure is negligible for compacted bentonites after correction. So if you see, they are just few kilopascals. That is that is not expectable, right, for compacted bentonites. So at present, what I'm suggesting is that we can completely avoid UCC and then directly estimate the diffusivity or diffusion coefficient of water molecules. And there are independent tests, in fact, as I mentioned. One is imbibition technique, or another one is we haven't published yet, but this is similar to what you do for contaminant transport. So from there, you can establish the diffusivity, and you can solve the flow equations, fixed diffusion equation itself, because you know the diffusivity is same as the diffusion coefficient of water. So now you can solve, and you will get flow problem solved. It could be 2-dimensional or it could be 3-dimensional. Anything can be solved because diffusivity is same in all the directions if you have a homogeneous bentonite compactor. It takes around 10 days in bentonites. You can speed it up if you take, even if you maintain a larger head, also doesn't make any difference, because flow characteristics depends on the hydraulic conductivity. Hydraulic conductivity is typically very less than 10 power minus. So whatever the head you maintain, you cannot do anything. So we cannot accelerate the process. It takes about 10-12 days, but highly compacted, maybe 1.8 megagram per meter cube if you compact, it takes way more than 15 days. In that case, you need to add penicillin, other thing. Otherwise, there is a microbial effect and PEG solution will enter into your bentonite. You will not have correct measurements. Yeah. This is only one point you are getting, because you maintain certain concentration of the PEG solution and you are waiting for equilibrium to take place between the soil sample and then the PEG solution. So once equilibrium takes place, this is only one point, because you are getting only one suction, one weight, that is moisture content. Again, you need to do another test by changing the PEG solution concentration, or a new test has to be started with changing the PEG solution concentration. You will get another section, right? It's a time-taking process for bentonite.